Hello again. Um, okay, so I did just come out of doing an A-level maths past paper. Hopefully this is working. Um, yeah, that's fine. So now I'm going to do some further maths. So obviously I think there's the first corporeal pure exam on Tuesday, and hopefully by now you have a good grasp of the topics. And you practice a lot of past papers. Now, I did hear 2023 was quite a rough one. So I think if out of any of them, let's do 2023. But yeah, the aim of this is be doing a stream tomorrow and Tuesday, not Tuesday, that'd be pointless after the exam. Today and tomorrow, which is Monday. Hopefully, we can get through both the papers of 2023. But if there is anything else that I can go over, if there are any questions, obviously let me know because obviously that's the whole point is to help people out. But yeah, without further ado, to save on time, I'm going to start with it then. Okay, so question one, quite a standard roots of polynomials question. We've got a cubic equation, and it says without solving the equation, find the roots of alpha plus two, beta, and gamma plus two. Okay, so if the roots are alpha, beta, and gamma, that means if you substitute this in place of x, that will be the roots that satisfy. That's not gamma at all. That'll be the roots that will satisfy this that you plug in to get 0. Okay. Now, if we shift our roots to be a plus 2 each side, well, you're saying that essentially x plus 2 is a new quadratic w, right? This is to shift. Okay, so if we then substitute x um, as w minus 2, that'll be the roots, right? And x here, which is substitute in for x here. So therefore, of w minus 2 squared, cubed, sorry, minus 7 w minus 2 cubed squared, minus 12 of w minus 2 plus 6 is 0. Really, at this point, it's just an expand and simplify exercise, really. So w minus 2, w minus 2, w minus 2, minus 7, w minus 2, w minus 2, minus 12, w minus 2, plus 6 is 0, and then we just expand, okay? Um, so w minus 2, and then let's expand this. So w squared, minus 2w minus 4w plus 4, minus 7 of, again, w squared minus 4w plus 4, minus, and then we're going to expand this, so you're going to left minus 12w plus 24 plus 6, that will be plus 30 equals 0. Okay, and then we can expand this again, so you get w cubed minus 4w squared plus 4w minus 2w squared minus plus 8w minus 8. And then we expand this, so then we left with minus 7w squared plus 28w minus 28. Let's bring it here. Minus 12w plus 30 equals 0. Now we just bring all the terms together. So w cubed is only one cubic term. And then minus 4w squared. Make sure it clear as minus 7. Minus 4w squared minus 2w squared is minus 6. Minus 7, that'll be minus 13w squared. And then let's collect all the w's together. So 4w, 8w, 12w. 12 plus 28 be 40w minus 12, that'd be 28w. Okay, and then we just add the constants together. So there's minus 8, minus 28, that would get you minus 36. Add 30, that'd be minus 6. And that, I believe, should be the cubic, right? That'd be the cubic, so the roots are x plus 2. So alpha plus 2 in replace for x. This, if you substitute this for w, this will give you the new roots, okay? But that should be a very, very, very standard exercise, right? A very standard question if you practice before. Okay, let's have a look at the next one. Okay, okay, we've got this one. Write this in the form here. So you should realise this is completing the square. So x squared plus 4x minus 5 is the same as x plus 2 squared. So remember you halve it, and then you minus the square. So minus 4 minus 5. X plus 2 squared minus 9. That's 1 mark. Pretty simple. Then it says, hence use the standard integral from the formula book. So we're going to need the formula book to find an integral that we can use to work this out. Okay. And we're going to need to use part A because it says hence. So it's going to be root x squared plus 4x minus 5 dx. Okay. Wow, this is the same quadratic we had, right? And actually, if I'm honest, they're really nice here, asking you to complete the square first, rather than implicitly expecting you to do so. But anyway, let's just substitute that in. So that's root of x plus 2 squared minus 9 dx. There's nothing more we can do at the moment, perhaps. Let's look at an integral, right? Let's look at the formula book of integrals that look like this. So it's probably going to be in the further math section. Uh, uh, Here we go, the integrals. Okay, so it was root 1 over, what was it, x plus 2 squared minus 9? Something like that. What looks similar? Well, actually, bear in mind, by the way, we can split the root up, so that'd be 1 over root of this. Okay. Because remember, root 1 is just 1. Anyway, so what looks similar? So x squared minus a squared. Well, yes, it does. This is a square number, as is this. Minus 9 is minus 3 squared. So I think this formula here is useful here. Okay, let's bring that in then. So well, that's going to be the integral of, and so you can just replace here x squared with x plus 2. You might be inclined to use perhaps the u sub, but if the u sub would be x plus 2, right? However, if you differentiate it, that'd be 1. So du by dx uh, would be 1, so du would be equal to dx. And we're not, so essentially, it would be exactly the same. We wouldn't change the integral at all. It would just be 1 over root u minus 9. But that's exactly the same form. So with these integrals, you can literally replace x plus 2 uh, as x here, and it'd be exactly as you'd expect because of that little quick use of thing there. But again, you should be quite familiar with that by now. But yeah, so that's the idea. So what's the integral then? Literally copy and paste it. So the integral would be, obviously, r cosh, was it? Of what was it? X over A? X plus 2 over 3? What was it? Remind me. If it loads, the formula book. Oh dear. Uh, Here we are. So x squared minus a squared. R cosh of x over a, which is alternatively this. Okay. So that's going to be x plus 2 over 3. Yep. Cool. Plus c. Okay, so that's just using a standard formula book. Quite nice. Then it says determine the mean value of this. What do I notice here is that this is in terms of logs. But hang on, we'll leave that in a minute because I'm thinking convert this to the log form, which is also in the formula book. But anyway, part two. So the mean value of this function. So you should know the mean is 1 over b minus a of the integral b to a of the integral we have. So 1 over root x plus 2 squared minus 9 dx. Okay, so what is our b and a? So it has to, the mean has to be along an interval, but we have an interval, it's between 3 and 13. So b is 13 and a is 3. So actually, 13 minus 3 are between 13 and 3 of this integral here. Uh, dear. Okay, so that's going to be 1 over 10, 13 minus 3 is 10, of r cosh of x plus 2 over 3 between 13 and 3, because that is that integral we worked out before. Okay, so that's going to be 1 over 10 of r cosh. Now 13 plus 2, which is 15 over 3, which is 5, minus r cosh of 3 plus 2, which is 5 over 3. Okay, so we can't do anything more of that as it is, but it says give an answer in this form a ln b, so it's in logs. We need to get this to logs, but also, and you should remember this, what's in the formula book, the alternative um, to arc cosh x over a is this. Arc cosh x over a is equal to ln, and we're going to write that, we're going to note this down. But arc cosh of x plus 2 over 3 is ln of here. So ln of x plus 2, so we replace for x plus 2 plus our square root, right? So no, sorry, we're not doing x plus 2, are we? Because we've got numbers here. So let's just do x over a is ln of x, what was it, plus root x squared minus a squared? Was that the answer? X plus root x squared minus a squared. Cool. Okay. And that's what we're going to do here. Therefore, mean is going to be 1 over 10 and arc cosh of 5. So substitute 5 over 1. So a is 1, ax is 5. That's going to be ln of 5 plus root of 5 squared minus 1. So it's going to be root 24 minus ln of 5 over 3, so that's going to be minus arc cosh 5 over 3, that's minus ln of 5 plus the root of 25 minus 9, which should be root 16, which should be 4. Okay, so it's 1 over 10 of ln 5 plus root 24 minus learn 9, which would be 1 over 10 learn 5 plus root 24 minus a tenth learn 9. Okay. What's the answer? Because that's not the answer, is it? A learn B. Right, okay. Oh, okay, so actually, we shouldn't do that. It's a big no-no. Well, no, we can do it. I'm just mean. No, it's only one log. So if we subtracting two logs, you can divide them. So 5 plus root 24 over 9, which is 1 over 10 learn 5 plus root 24 over 9, just getting rid of the brackets. And that is in the form A learn B, with A the 10th and B is this number here. 5 plus root 24 over 9, okay? So that's the answer to that. Let's make that a bit clearer. So yeah, so not too bad of a question, right, so far. Lovely jubbly. Okay, question 3, part A. Express Z1 in the polar form, r cos theta plus I sine theta. So, we are given the Cartesian x plus I y form. We should know how to convert that into our argument polar form. No, that's not the answer. Modulus argument form, so the polar form. So the way to do this is I think the best way is to plot the number. Uh, so this is obviously the real axis and the imaginary. So -4 would be over here, and 4i would be up here. Okay. The argument is going to be here, right? This angle here. This whole angle when we go from 0 to here. I should probably say that's 4i and that's -4. So the argument then, if we then call oh god, what have I done now? If we then call this little bit theta between the imaginary axis and here, the argument is going to be the first pi over 2, 90 degrees, because we're going from the real positive. So we measure every argument of a complex number from the real positive axis. So from here, and then we go this way. Okay, so we go anti-clockwise. So it's the first 90, so pi over 2, plus theta. And theta is just simple trig, right? So this is the opposite, and this is the adjacent here. Okay, so tan theta. Alternatively, you should know the tan theta is always y over x. Okay, so the imaginary form over the number form. Okay, so anyway, tan theta is 4 over 4, which should be 1. And actually, that means theta would be pi over 4. So therefore, arg of z, well, it's going to be pi over 2, it's pi over 4, which will be 3 pi over 4. Yes, so, cool. Alternatively, well, I guess this is -4, right? So it would be 4 over -4 of tan theta. if you decide to not sketch it, that would be you'd get minus pi over 4. Okay. Um, that obviously doesn't make sense because minus pi over 4 would be here. Because obviously, alternatively, this is the positive direction, if anti-clockwise. If you go if you go clockwise, you'll go negative pi. So negative pi over 4 will be this number here. So you need to be careful of where you place your arguments, okay? That's why you must sketch your arguments. Because the complex number of minus 4 plus 4i is over here, not over here, okay? And actually, there are two solutions to this. So this is true, but I guess let's have a look. So the tan graph, remember, look like this. When it's minus 1, because minus 4 over minus 4 is minus 1, asymptote there, asymptote there. Then there are multiple solutions, right? It's minus pi over 4, or the next solution by adding 180. So then you'd get 180, or pi, I should say. So the next solution to this angle theta is pi minus pi over 4, which should also be 3 pi over 4, which is the answer here. So this is true. You can solve it by just doing what the imaginary component divided by the real component. So you could do 4 divided by minus 4 instead of just 4 over 4 to find this angle here. But you need to consider where the theta is, so where the complex number is. If you just took minus pi over 4 by arctanin, that would be this number here. But then you need to consider other solutions for theta. So the next one would be like here again. If you draw the tan graph, when tan x theta is minus 1, the next solution would be next 180. So then that would be 180. And obviously it repeats every 180. So minus pi over 4, add pi, which is 180 degrees. That is the true argument here, which we've got here. That would place the angle over here. Hopefully that made sense there, and why it's a good idea to sketch the complex number, okay? But yeah, there's two ways of working out the argument, and I think the argument's the most fiddly one of a part of like a complex number. Well then the modulus, well it's a modulus, right? You just do the Pythagoras, so it's going to be the distance of the x and the imaginary and the real components, kind of like how the distance of or the position vector or the length of a vector like a it's just you square all the x and the y and the z components or the I, J, K note components. Same premise here. So you're going to want to do 4 squared plus minus 4 squared, I guess, if you wanted to. Well, that's going to be root 32. 16 plus 16 is root 32. Which means obviously z is then going to be root 32 of cos of the argument, which is going to be 3 pi over 4 plus I sine 3 pi over 4. Lovely jubbly. Okay, not too bad either, as long as you pay attention to like the parts where the complex number is. Anyway, so we got that. Now we told another complex number in this form. Then it says determine in Cartesian form. First of all, the division, okay? So Z1 divided by Z2. Uh, well, you should know that when you divide two complex numbers, if they're in this sort of form here, with a length or the rate or the modulus with the angle, you divide the modulus, so the r's. So root 32 is the length of z1, and the length of z2 is 3. Okay, and Then, when you divide this part, you want to subtract the angles, okay? So cos of 3 pi over 4 minus, and then what's the angle Z2? 17 pi over 12, okay. Plus I sine of 3 pi over 4 minus 17 pi over 12. Okay, and then we just simplify that. So we can't do anything more with this. Oh, actually, does root 32 simplify to anything? 4 root 2. Okay. 4 root 2 over 3 of cos. And then let's do this. So 3 over 4 minus 17 over 2 gets you minus 34. 31 over 4 pi plus I sine minus 31 over 4 pi. Now, the angle here really should be positive. I'm not sure that it's set. I think they might it's set. Oh no, it doesn't matter because it has to be in a real number. No, sorry, it needs to be in this form. Okay. But that would imply that what happens if you type in cos of minus 31 over 4 pi? Okay, nice. Um, so if you type this into a calculator, the cos of this minus 31 over 4 is root 2 over 2, and then plus I of, and then do the sine of that. Sine of minus 31 over 4 pi, and that gets you root 2 over 2 as well. Okay, and now you type, and then just expand it. So that simplifies to 4 over 3 plus 4 over 3i. And that is how you convert again from the polar form to just x plus y. So a normal complex number. Just expand essentially by computing what the cos of this is and sine of this is. Okay. So that's the real component, and that's the imaginary. Okay, that should be quite familiar, but that's how you do that question. Let me check I've done that right, hopefully. Um, oh, hang on. Oh dear, what's happened here? Okay, yeah, that's all right. Minus 17. Yeah, they did that. Cool. Wait, what's... Yeah, okay, I'm calculating radians. Why has it not got the right answer? Okay, so that's all right. So the mark scheme, that's interesting. I get different answers to the mark scheme. So put that again. So cos of minus 31 over 4 pi, that's root 2 over 2. And then if you times that by this, you'll get this, wouldn't you? Let me check if I've done this right. Hang on. I might have just not done the fraction bit. I probably just misread it as usual. 3 pi over 4 minus 17 uh, over 12. Oh, hang on. There we go. Okay, 3 over 4 minus 17 over 12. Okay, that's not the right angle. Okay. 2 over 3 plus I sine minus 2 over 3. I don't know what I did there. Now you put that into the calculator. Okay, see what happens. Okay, what's cos of minus 2 over 3 pi? That's minus a half. minus a half plus I of what? Minus root 3 over 2, so that's minus root 3 over 2I. I don't know. I don't know what happened there. I don't know. And then obviously then expand that out. So that is going to be minus 2 root 6 over 3I, and then times the minus a half. And then that's minus 2 root 2 over 3. And that's what the mark scheme has. Cool. Okay. And then I believe II, was it Z1 to the 4, was it? Was that it? I vaguely remember. Yeah, Z2 to the 4. Oh, okay. Cool. Wow, that's going to be Z2 times Z2 times Z2 times Z2. Now, if you remember, if you times two complex numbers, kind of like the reverse, you are going to times the modulus, the lengths together, and you're going to add the arguments. Now, if we're timesing it 4 times, we're going to have to times the argument, which was 3, 4 times, and then we're going to do cos of, and then we're going to do 4 lots of the angle, which was, what was it, 11, 17 pi over 12? Plus I sine 4 times 17 pi over 12. And so then if you bung that into the calculator, well, 3 to the 4 is 81. And then that's cos, actually, no. Let's work this out. So put that into the calculator. No need to do any more work than we need to. Cos of 4 times 17 pi over 12. That gets you a half. And then the sine of that, sine of 4 times 17 pi over 12. Gets you minus root 3 over 3. Okay. Root 3 over 2, sorry. And then expand that out. So 81. That's 81 over 2. Minus 81 root 3 over 2I. So that's cool. So that's part 2. Now it says for part C, showing a single arcane diagram, the complex numbers Z1, Z2, and the division, which we worked out in part BI. So let's do that then. And we already did plot Z1 already. So, part C. Let's draw a big argon diagram. So real, imaginary. So we know Z1 was minus 4 plus 4i. Minus 4 plus 4i. So that'd be about there. That's Z1. That's 4i minus 4. Okay, that's Z1. Now we need Z2. Now Z2 is written in this form. So I think the best thing to do is to again write in x plus iy form because everything else is in x plus iy form. So let's do cos of 17 pi over 12. I'm not sure this will give you a nice number actually. Well, it does, but it's still not nice. Okay, so that's about 0.776 plus, oh, minus 0.776 minus 2.898i. So that's roughly where we're standing. It does actually give you an exact answer, but it's not the nicest. And we don't need to give the number. We just need to plot Z2. Anyway, so minus 0.7, minus 2.8. Okay. So that's going to be like there. Minus 2 points. So Z2 is going to be like there. No, sorry, minus 2 points. Sorry. So that's going to be like there, isn't it? Minus 2.8, minus 0.7. So that's Z2. And then Z1 over Z2. Well, it's this. So this, which is approximate to. So let's convert this into an actual decimal so we can compare with the other numbers. Minus 2 root 2 over 3, which is minus 0.94. And then minus 2 root 6 over 3 is minus 1.63i. Okay, so it's going to be just a bit over Z2, and it's going to be on the real axis anyway, and it's going to be just above Z2 here, so it's going to be about there. So that's Z1 over Z2. Okay, so that's all it is. So it just said to plot them on the graph, right? Showing us them the numbers, right? There we are. If you wanted to, you could put like the relative numbers in. So what, minus 0.63, that's 0.9 something. But there we are. Those are the 3 points, right? Z1, Z2. I should make that quite clear. Actually, this is Z2, and this is Z1 over Z2. Okay. Cool. And then part II. We got this. The region defined by this. Z minus Z1 is less than Z minus Z2. Okay. Cool. Or alternatively, Z minus. Well, we don't really need it actually. So what this is saying, so in general, Z minus A is the geometric mean is the distance away from A. Okay. So if this is equal to 6, then that's telling you the distance of roots of 6 units away from A. Okay. So say Z1 is here and it was 2, it'd be like a circle with radius 2. Okay. And that's hopefully should be aware of that. But actually, it's telling us that this has been less than the distance of a number, a distance between Z and Z2. Okay. Uh, this is a very common one. I believe this is perpendicular bisectors, is it? Which makes sense because the perpendicular bisector, say if you have Z1 and Z2, obviously the perpendicular bisector, if you remember from GCSE, is obviously it splits it in half, but it's drawn in such a way such that everything on the left is closer to Z1 than Z2. And that's what we want. We want the distance. So this would be Z, right? This little line here, the perpendicular bisector. So this Z minus Z1. So the distance of points to Z1 is closer than Z2. So we are interested in this region here. So what we need to do is actually just plot again, a real and imaginary. Where's Z1? Well, Z1's up here. We did that already. Let's do this again. and Z2 is down here. Now consider the line that and river ruler anyway that connects it. So the perpendicular bisector would be something that looks like this, right? That's perpendicular. And that will be your region there. And actually, the shaded region would be the region here. Okay. Um. Actually, I think we need to be a bit more specific than that. That is the right idea. Uh, but I think we need to be a bit more like accurate. So with our placements of on here, so see here, Z1 is further away from the axis than Z2. So what do I mean by this? Well, let's draw this again. Uh, Imaginary. Z1's over here, right? Cool. Z2 is about here. Now Z2 is closer to the axis of Z1, so when we draw this line that connects them, the perpendicular bisector is going to actually not look like that. Sorry, it's gonna go over. Oh, my apologies. It's gonna go over here, so it's gonna cross the line in this quadrant here. So it's not going to cross the axis. It's going to be here. And so there's points again. Is this Z1, Z2? Like with this diagram here, it has to be on the side of Z1 in order for the distance between the points of Z1 to be closer to Z1. So say if Z is on the fence here, that's perpendicular bisector. It has to be closer to Z1. That's what this is saying. The distance between here and Z1. And for that to happen, that's the region here. Cool. Let me just double check that's right. Yeah, yeah. That's pretty much exactly what they're drawn. So they're drawing a perpendicular bisector. And yeah, that's the points here. Cool. So hopefully that's clear. So yeah, so you should be able to interpret. There's there's three cases. You have a half line. So arg z is like um less than or equal to or greater than an angle theta. Uh, you would have z minus a would be less than or equal to a number k, which would be a circle, or the z minus a is less than z minus another number b. So that would be the perpendicular bisector. So you need to be aware of half lines, circles, and perpendicular bisectors. In this case, it's a perpendicular bisector because you're looking at the distance between 2 points and you see which is closer. Okay. So you consider the line that connects the points. The perpendicular bisector is the equal distance between Z1 and Z2. It ensures the equal distance. Every point on this line is equal distance away from Z1 and Z2. So if you want to be closer to Z1, it makes sense it has to be on the left towards Z1. Okay, and that should be from GCSE. So yeah, I'm not going to go too much more into that, but that's the idea behind that. So I don't think that's a bad question. Obviously, I know I've misread a number. I must have put the calculator wrong. And now we got really another nice question. I mean, it's shaping to be not so bad paper so far. It's better than the paper I sat. I remember I did the 2019 one. I do think that was the hardest one so far. Don't at me on that. I'm not being biased there, but that was an awful paper. Even the standard questions were rough. But anyway, I'm going over this paper. You can beef me after. I'm sure a lot of people who did 2023 would not be happy with that statement. Anyway, so proof by induction. So you should know with induction, you need a basis and a step. You need an assumption, which is an induction step. So the basis, well, what's the first number of n? Well, n is a natural number. That's what this means. Natural numbers is obviously. Let me draw that better. The natural numbers is. Oh god, that's horrible. I'm trying to draw this fancy little n here. There we go. It's about as good as it's gonna get. That's 1, 2, 3, 4. I can't write. So on. So obviously the starting point is 1. So that's what an assumption is. Then assumption is for any integer k, that is a natural number. And then an assumption is you're using n is k plus 1. That's the whole idea of this induction process. Just to give a brief explanation behind it, it kind of makes sense because say you have a statement P of n. If you assume, no, sorry, so if you assume for some integer k is true, and you prove the next number is true, so these two are true, right? Then we can use k plus 1 as the assumption of the next number k plus 2. And in the same way, if k plus 1 is the assumption and we know the next number is true, that means this can then be the assumption, which we know is true for the next number, pk plus 3. And therefore, we know the next number after the assumption is true. So if we assume any given integer is true for k, and we prove the next number onwards is true, then we can kind of create this chain of reasoning, right? So if we know that an initial integer k is true, and then the next number is true, well, this can be the assumption step for the next integer. So if the assumption is true here, k plus 1, which we know is true, then the next number has to be true. And then if we use this as an assumption for the next one, so k plus 2 is true, if we set n as k plus 2, and then the next number is true because of the induction. And it keeps going on, and actually, because of this line of reasoning, every possible whole natural number integer is true, has to be true, right? Because of this chain of reasoning, okay? Um, but the only question is, we need to know where to start this rate chain of reasoning because we're given a generic number k here. So once we kick off the chain, so we know that if we assume an initial number is true, and then the next number is true, we can keep continuing on to the next and the next and the next number for every integer. But we need to know where to start, and that's where this basis is. This basis gives us a the first where tells us where to start this this chain of reasoning. So if we start from an initial number, which we know is true, it's not an assumption, but we know is true. So p of 1. Well then, if we assume n is 1 is true, so k is 1, and then we prove the next number, p of 2 is true, and then we can start the chain of reasoning again. So then we assume p of 2 is true, which we know it is. Then p of 3 is true because the next number of an assumption is proven to be true because of our induction. And then p of 4 is true, p of 5 is true, and then the chain of reasoning goes on and on and on. So that is just a general rundown of the idea of induction. But really, with these, with further maths, with this course, really they just expect you to know the method and how to prove stuff and apply the proof, essentially, using a certain method. Um, so that's just the intuition, the explanation behind it. But that's what we're going to do essentially. Start with a basis and then work our way forward. So basis step. And because it is a proof, you do need to be a bit clear of how you write stuff. So let n equal 1, because obviously that's the basis. Then, well, start the left-hand side then. 1 minus 2, 0, 1 to the 1. Well, that's simply 1 minus 2, 0, 1. And 1 minus 2n, no, minus 2 of 1, 0 of 1, oh god, make that clear, equals 1, minus 2 times 1, that's minus 2, 0, 1. And Bob's your uncle. So LHS equals RHS. They will know what you mean by LHS on the right hand side. They will know what you mean. You can say it like this. Is true for n equals 1. Therefore, statement is true for n equals 1. So we found a base case, right? We found where we could start our induction. So then the assumption uh, uh, step is assume statement is true. So this equation here essentially is a statement, right? It's an alternative way of saying it. So assume the statement is true for any given integer n equals k. What does this mean? Well, so the matrix here. Uh, um, so 1 minus 2, 0, 1 to the k is 1 minus 2k, 0 and 1. Is true. So this equation holds, right? For this given integer k, that's our assumption. Now our inductive step, let n equals k plus 1. Thus, and this is where we're going to start to combine stuff together. So the idea is now at this point we work with the left hand side and then we arrive at the right hand side. Okay, so we're going to need to look like, well, if you substitute k plus 1, we're going to need this number here, not number, matrix here, to look like 1 of minus 2 of k plus 1, 0 and 1. Okay, that's what we're going to need to get at the end of this. Anyway, so 1 minus 2, 0, 1, k plus 1. Again, like with a normal number, you can split up the matrix as follows. 1 minus 2, 0, 1 of k. 1 minus 2, 0, 1. But we know what this is. This is our assumption. So the idea, again, with induction, you need to apply your assumption to the induction, because that's the whole idea. Okay. But we can use this, so we can substitute it. So that is 1 minus 2k, 0, 1, of 1 minus 2, 0, and 1. And so what can we do now? Well, it's matrix multiplication. So for the left row, 1 times 1 is minus 2k times 0, that's just 1. 1 times minus 2 times minus 2k, so that's minus 2 minus 2k. Okay, and then here, 0 times 1 plus 1 times 0, 0. 0 times minus 2 times 1 times 1 is 1. Okay, now let's factorise. This can factorise, bearing in mind the form we want it in. So that's going to be 1 of minus 2 of k plus 1, 0, 1. Hopefully you're happy with that. Well, this is not exactly the form we wanted. Here, minus 2 of k plus 1. Yes. Yes, it is. So we've done it. Therefore, the statement is true for n equals k plus 1, as obviously LHS is equal to the right-hand side. The left-hand side's here, it's the same as the right-hand side. There we go. So that, and this is the conclusion, right? Therefore, as the statement is true for n equals 1 and is true for any integer n equals k plus 1, provided it is true for n equals integer k and n equals k. That means, again, by our chain of reasoning of the idea of proof by induction, then it has to be true for any integer n greater than or equal to 1. So n is 1 is our basis, and every number after that, by a chain of reasoning, the chain and chain, it'll be then be true for every number after 1 as well. And yeah, that's the idea behind that. Okay, I'm going to look at the last question, but it's a meaty question. I'm going to leave that till next time because it's getting late where I'm from. But yeah, so that's probably just under half the no, not under half the paper. But yeah, so that's the first part of this. I'm going to do the next part of this paper tomorrow if you're watching in real time. So this is part 1. I'll get the next part done tomorrow. And then I'll try and look at the paper 2 as well. Hopefully I have enough time for that. But yeah, so that's the first part, just going over stuff like that. Going over the first 4 questions. Not bad so far, if I'm honest. Pretty standard stuff. So yeah, hopefully this will make sense so far, especially for exam on Tuesday. Um, uh, but yeah, I'm going to leave that there. And then, like I said, any questions, anything you need to go over, if I can help you in any way, let me know in a comment or whatever. But I am going to leave that there, and we'll pick this up next time. So yeah, see ya, and good luck on Tuesday as well.